Oh, I need to record this. If it's called must know functions, then Chandler, you are absolutely right. You must know these functions. Okay? Yeah, put it in the cycle. You must know them forwards and backwards and in between. That's exactly right. These are very, very, very important. Okay? These are what we call, we're going to look at what we call the parent graphs. Oh, y'all try to contain yourselves a little bit. So one that you're very familiar with would be the quadratic, okay? And parent graph is before any transformation is done to it. Before you've shrinked it any, stretched it any, shifted it any. So if I'm talking about something with like quadratics, then y equals x squared would be the parent graph, okay? And then as we do things to the parent graph, it changes shape and direction and what it looks like, okay? So we're going to talk about 20. I'm going to give you 20. There's 12 in the book. I'm going to give you 20 to look at. But I'm going to give you this little packet after we go over everything. All right, we're also going to redefine a couple little things ever so slightly. We've talked about continuity extensively, right? Yes. And so we're gonna kind of expand on our definition of continuous. So for continuous from now on, we're going to say that a function is continuous. Function is continuous. Remember before, we're just talking about how we draw it and what it looks like. Now we're going to say that it's continuous if every point in the domain is continuous. Now, I want you to think about that for just a second and what that means. When I am talking about an infinite discontinuity with a vertical asymptote, right? Say something like this. Okay? And I said, is that function continuous? You would probably say, well, it has an infinite discontinuity. Go ahead, you can sharpen your pencil. And I would say, okay, let's don't think about infinite. Let's think about the definition of continuous. Is every point in the domain continuous? And so maybe let me give you this equation. Let's say it was 3 over x minus 2. Okay, so this is 2. When you find the domain of this function, what is the domain of this function based on the equation? What about x minus 2?
It's 8.
But what does the domain? You see a fraction there. Tell me about the domain. It can't have 0 in the bottom. What can't be in the domain? 2. X minus 2 can't be 0, which means that x that can't be 2, which means my domain is negative infinity to 2 and 2 to infinity. So my original question goes back, is that function continuous? Well, look at the definition of continuity. It's continuous if every point in the domain is continuous. Well, the only part that's not continuous is what? Is that in my domain? Look at your domain. Is that in your domain? I left 2 out of the domain. Since I left it out of the domain, then I can say, yes, this function is continuous. Why? Because it is continuous for every point in the domain. Okay? Does that make sense? If the discontinuity, okay, do you see the discontinuity, Olivia? The discontinuity is the vertical asymptote, right? If you leave that out of the domain, like I did here, you leave that out, then it does not affect its continuity. It does not make it discontinuous because I didn't include it in the domain, okay? Now, if the domain was negative infinity to infinity, this would be a discontinuous function, okay? That's right. But because the domain is negative infinity to 2 to infinity, then it doesn't include that piece, so it is considered continuous, okay? Do you understand how we're kind of redefining this? We're not looking at places that are left out of the domain. Let me show you another one. Let's say f of x equals, we're going to do a piecewise. And I'm going to talk about piecewise a little bit more, but we have talked about it a little bit in here. Let's make this one greater than 2. Come on. Let's make this one less than or equal to 2. All right, so I've got these two pieces of graphs, okay? And so we've talked about when we graph these, this is a line, right? But only when x is bigger than 2. So I want to plug in when x is 2, what is y? Y'all can do this. What is y when x is 2? This is your equation. If you plug in 2 for x, what is y? 6. Right? Yes? So this is two different equations. This is saying f of x equals x plus 4. And the second one is saying f of x equals 4 minus x squared. Huh? Okay, I'm explaining. F of x equals x plus 4. I'm breaking them out, okay? But this is only true when x is greater than 2. Okay? So if I want to know what is x equals 2, I plug it in. 2 plus 4 is 6. So I get the point 2, 6. 1, 2, 6. It's an open dot because there's no line under here. Right? And if x is greater than 2, then it means x can be 2 or anything bigger than 2. Give me one that's bigger than 2. 4. When x is 4, what is y? Same equation, 8. That's what that piece of the graph looks like. It's called piecewise because it's two different pieces of two different graphs, okay? If I had graphed that whole line, it would have a y-intercept of 4. This is why we spent so long in that preliminary section graphing lines, okay? It would have a y-intercept of 4 and a slope of 1. That's what it would look like. But it tells me that x is greater than or equal to 2. It's restricting the domain. So I do away with anything that's not greater than 2. I picked an x that's bigger than 2. Could have picked 3. Could have picked 5, whatever you want. Okay? Because it was a line, I really only needed 2 points to make the line. Okay? I just need to make sure that it goes off in the right direction. Okay? For the second one, look at what it's telling me. This time x has got to be less than or equal to 2. Okay? So I'm going to plug 2 in. What happens when you plug in 2? You get 0. Okay? 2, 0. And this is a closed dot. Closed dot because of this line under. Okay? Now it says that x is smaller than, but this is a parabola, so I'm going to need more than just one more point. I'm going to need to keep going until I find the vertex and keep going, right? So what happens if you want to do a little t-chart, do a little t-chart. Okay? I plugged in 2, I got 0. We got to go less than, so what happens when x is 1? What is 4 minus 1 squared? 3. Well, no, because you're subtracting, so this is really like this. How about 0?
So where did you get that other point?
Which other point? This one? I plugged in 4. We're going to have to look at piecewise a minute. I can see that. I said we're going to have to take a minute and digress and look at piecewise for a second. So, think about it like this, okay? Jackson was asking about this first one again, okay? If I graph the line, if I graph this line, x plus 4, that would be a point at 4, up 1 over 1, up 1 over 1, right? That's what this line would look like. But then it says, wait, you can't have any x unless it's bigger than 2. So, really, you're just erasing this part of the line. Because this is where x is 2. Okay? To save from all that trouble, what I did was I just said, well, I'll just start at 2, and I'll go up from there. So I don't have to erase anything. Same thing with this parabola. I'm starting at 2, but because x is less than 2, I'm going below 2 as I plug in points. So I did 2, 1. I'm going to do 0 next. What's 4 minus 0 squared? 4. Remember, this is a piece of a parabola. So I need to keep going until I've at least found the vertex and start coming down. So how about negative 1? What do you get? 4 minus negative 1 squared. 3. Remember your order of operations. Yes, but with the restricted domain. Do what? Both of them just for, but you just have to look at the numbers at which way your domain is going. Now look at the function as a whole. Okay. First of all, is it a function? Why? How do we check functionality? Not continuous, but function. What's it mean to be a function? It passes what? Vertical line test. Does it pass the vertical line test? Look, this is the only place that it might not pass the vertical line test. But since this point is open, it doesn't include that point. So it makes it a function. Okay? Now, because this was just greater than, it wasn't greater than or equal to. Is it continuous? Now remember, continuous means it's continuous for every point in the domain. What's the domain of this function? Is anything left out of the domain here? No. It's negative infinity to infinity, right? Both of these make up the function overall. So there's a point, everywhere left to right, there's always an x and there's a one y and only one y that's defined at that x. So is it continuous? No. Why? Where's the discontinuity happening? 2. At 2. What kind of discontinuity is it? A jump. You see, the difference in this one and the one before is my function was defined at x equals 2. That's where the discontinuity happened. If I told you that my domain on this was negative infinity to 2, 2 to infinity, then it would be continuous because it would leave that discontinuity out. But because that's in the domain, I have to include it here as I look at continuity. Does that make sense to you? Let me look at one more piecewise with you because I think we're struggling piecewise. Let's say I'm going to call this piecewise. F of x equals x minus 2 when x is, come on, greater than 1 and, oh no, x squared when x is less than or equal to 1. So I want you to graph that function and then we're going to look at the domain and the continuity there. Put that away because that is not going to help you with that phone in that computer. All right, so that's exactly, Jackson, what I would do first. Graph each one separately. So, yes, the first one I would do I would plug in 1, and then since it's a line, 2 points is sufficient. So plug in a 2. When x is 1, all I'm doing is plugging in here. 1 minus 2 is negative 1, and 2 minus 2 is 0. Is everybody with me on that? Okay. Do I start with an open dot or a closed dot at 1, negative 1? Why? It's not or equal to. 2, 0. Do we all see that that's when x is greater than 1? X gets greater to the right. That's that piece of line. That's why it's called piecewise. It's a piece of a line and a piece of a parabola put together for one function. Okay? How about the second one? I have x squared. What should I start with? Somebody said it. 1. And then I got to go down from there, right? Because it's less than or equal to 1. 0. Maybe negative 1. I don't know how many I'm going to need until I plot them and see what the pattern is here, right? Now, if you want to go through and find the vertex, see where that happens, that's fine too. 1 squared is 1. 0 squared is 0. And negative 1 squared is 1. You see I found that vertex. 1, 0, 1. All right, so 1, 1. 0, 0. Negative 1, 1. It goes off this way, but not this way, because it's a piecewise, right? It cuts it right there. Is it continuous?
Wait, hold on.
What's the domain? Because that's going to help us with the continuity. Negative infinity to infinity. Look, this might be only defined when x is greater than 1, but this is defined when x is less than or equal to 1, so every number is included. So my domain is negative infinity to infinity. So is x defined at every x in its domain? Or is x continuous at every point in its domain? Is the function continuous? Can't get my words out this morning. No. I have a discontinuity here, right? The function is defined at x equals 2. I mean, x equals 1. But it's not continuous there. So that means no, it's not continuous. It's a jump discontinuity. Y'all good? Somebody said wait. Let me show you uno mas and let's see if you understand piecewise. You try to graph this one. This one will be easier. A little bit easier. I want you to graph it and then tell me if it's continuous or not. I say it's going to be easier. Does it matter how many pieces I have? And analyze it. Look at what kind of functions you have. What's the first one look like? If you didn't have any domain restrictions there, what's the first one look like? What's the graph of y equals 4 look like? So straight line which way? What kind? Horizontal line at y equals 4. Straight across. How about 2x? What does that look like? It's a diagonal line, right? How about 5 minus x squared? What kind of graph is that? Anytime you see a squared, it's a parabola, right? So I've really just got 2 pieces of lines and a piece of a parabola, which is what I've been doing. I've just got an extra piece of a line. So think about that as you graph. Well, it'll be a horizontal line at 4, but only between the values of -3 and 2. All right, look at the first one. I hope you've at least gotten through the first one here. Tried to. X is less than or equal. Remember, we only need 2 points for lines. So the first 2 equations I know I'm only going to need 2 points for, right? Definitely -3. And what else did you choose? -4, smaller than. It doesn't matter what you plug in for X. What's the value of Y going to be? 4. Y is always 4. The equation is y equals 4. Because no matter what x is, y equals 4. X is 100, y is 4. X is 2, y is 4. Doesn't matter, y is 4. Okay? Well, 1 is not smaller than -3. You got to go in the right direction because you got to cut it off in the right place. Yeah. You got whatever it tells you to do. That's what your x has got to be. Yes. Yeah. How come I got what? Because I went less than -3. Nope. You could have chose -10. As long as it's smaller than -3, because it says x has to be smaller than -3. So I'm going to use those 2 points. Remember, it's a horizontal line, okay? So -3, 4. Is it closed or open? Closed, because it includes, right? And then -4, 4. That's what that piece looks like. It goes on forever for every single x that is less than or equal to negative 3. All right, how about the middle one? What did you plug in? Negative 3. It's a line, right? So you need 2 points. Because this is between 2 like this, what else did you plug in? I would plug in, okay. Reason being is you want the 2 endpoints. This doesn't go on forever in one direction. It's just between 2 values, okay. So I just want between those 2. This is between negative 3 and 2. Negative 6. X less than or equal to 2 is how you read it. But how you interpret it is that X is between negative 3 and 2. Negative 3 is the smallest X can be, and 2 is the biggest X can be. So it's got to be in between those 2 values. Negative 3, negative 6, open or closed? Open. And you see why right above it here I have a closed dot. I can't have closed dot on closed dot or it wouldn't be a function. And then 2, 4, open or closed? Closed. There's another piece. And then my very last one is the hardest because it is a parabola, which means I have to pick up more points than with a line. What's wrong? If there's a line under it like this, it's closed. I'm going to go 2, 3, 4 and see what happens. That might be enough and it might not be. 5 minus 2 squared is 5 minus 3 is squared is 5 minus 4 squared is I don't have enough. I haven't dipped and started coming back up. So let's see. How about 5? It'd be 0. How about 6? 5 minus 6 is negative 1, and negative 1 squared. Now I'm dipping back around. Do you see how I told the numbers were going down, 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 and then they started going up? That tells me I have enough points. Okay? I'm definitely going to plot the 2, 9. 9. Open or closed? Three, 4, 4, 1, 5, 0, 6, 1. You can see the pattern here. It's a terrible parabola. Terrible. But again, what's the domain of my function? That's correct. Negative infinity to infinity, right? Well, is it what now? Say that again. No, it's still negative infinity to infinity because every x is included left to right. How about continuity? Is it continuous? No. Because every x is included in the domain, but yet, if you look, I have some jump discontinuities, right? How many discontinuities do I have? Two jumps, right? All right. Let's talk about the parent graphs. I have these typed up for you, but I want you to write these down, and I'll give you the typed up version after we're done. All right, parent functions. These are your must know. And you must know the analysis on these, backwards and forwards, the way the graph looks, everything about them, okay? Some of these are Algebra 1 functions, some of these are Algebra 2 functions, okay? So if you don't know them, you're going to really have to study them, okay? Because I won't be able to go back and reteach every single function. But I've got some steps on here as to how they're graphed. All right, so the first one is a linear function. Parent function is y equals x, okay? It is a line with a slope of 1, a y-intercept of 0. It is your most basic linear function, okay? As we start doing things, I'm missing so much here. As we start doing things to it, it changes. The slope can change, other things can change. But for right now, that's the parent function. Let's see what it looks like. If we were to graph it, tell me what you do first to graph this. How do you graph this line? Y equals x. Anybody? It's just a straight line, but how do you graph it? If I gave you a test right now and I said graph this line, what's the first thing you would do? 0. You're absolutely right. 0 is the y-intercept. I would put a point at 0. Then what do you do? Ooh, if y'all can't graph a line, y'all not going to do good in this chapter. You go up 1 over 1. It's the slope of 1. I just need 2 points, right? Because it's a line. What's the end behavior of this function? Oh, y'all thought all that was going away, and unfortunately it's back. It's back. As x approaches positive infinity, as x approaches negative infinity, what's the domain? Somebody said it. Negative infinity to infinity. What's the range? Is this continuous? Why? Straight line. You don't have to pick up your pencil. And more sophisticatedly, for every point in the domain, the function is continuous. Okay? Y'all with me? Is this function symmetric? And if so, what type of symmetry does it possess? Odd. Why is it odd? So if f of x is x, then f of negative x is negative x, right? So is that the exact same equation, the exact opposite equation, or is it neither? Opposite. The exact opposite, which means it is an odd symmetry. So x going to positive means the right side. So the right side of the graph is going up. X going negative is the left side, and the left side, the graph is going down. Yes. All right, let's do next parent function. I put my pen? Parent function number 2. I don't know what is wrong with this stupid screen. It does not want to do it today. What function is that? What changed? Somebody said it. It's absolute value. It does change the sign sometimes. When does it change the sign? When it's negative. It makes it always positive, okay? You may not be as familiar with what this graph looks like. Okay, so I'm going to tell you how to graph this. What we do is we start, your vertex is going to happen on this one. Remember, this is a parent graph, so nothing's been done to it. We're going to really work with transforming functions soon, so you have to know the parent graph, okay? So at 0, 0 is where it starts. What happens if you plug in 1 for x? What do you get? What do you get? What's 1? No. If you plug in 1 here, what does y equal? 1. What if you plug in negative 1? It's 1. That's what this graph looks like. Describe the end behavior of this graph. As x approaches positive infinity, is this function continuous? Why? It is continuous for every point in its domain. Get used to saying that, because when I ask you why, that's what I want to see on a test, okay? Yes, because it is continuous for every point in its domain. Yes, so what's the domain here? I should have done that first. Negative infinity to infinity. What about the range? Look closely. Bottoms up. 0 to infinity.
Wait, the range is the lowest though?
Up to the highest. Is it symmetric? What type of symmetry does it possess? Ooh, good job. It's even. It is even because if f of x is the absolute value of x, if you plug in negative x, you end up with the exact same thing you started out with, which means it is even. You can also look at this and tell that it is symmetric about the y-axis. All right, I think I'm going to stop there, and I think we'll finish the other 10 functions tomorrow, because then we start getting into some, we got quadratics and we got radicals and cubics, but we'll get into some that are not quite some trig functions and stuff that I think we'll skip over for right now. And we'll get to tomorrow. So what I'm